Hi everyone, this is Sheikh Roshan Zamir from CAC department. I am going to explain about response to scale up or scale out for graph processing. Introduction to graph processing. Graph processing refers to the computational handling of graphs, structures composed of nodes and edges. Applications range from social networks to biological data, where relationships and connections are crucial. Graph processing challenges. Challenges include large datasets, nodes and edges, high computation complexity, efficiently managing memory and resources, real-time process demands, scale up versus scale out. Key differences. Scale up. Increase power of single system by adding more CPU, memory, etc. Scale out. Distribute workloads across multiple systems or nodes in a cluster. Scaling up for graph processing. Scaling up relies on improving hardware resources within a single machine. Advantages: simplified architecture, low latency, easier to manage resources. Scale out for graph processing. Scaling out distributes tasks across multiple machines in a cluster. Advantages: can handle larger datasets. Redundant systems improve reliability. Cost effective scaling with commoditative hardware. When to scale up? Scale up is preferable when the graph size is manageable, latency is critical. There is a need to minimize network overhead. When to scale out? Scaling out is ideal when the graph dataset is large and complex. Horizontal scalability is needed. The system needs to handle large scale distributed data. Graph partitioning. Graph partitioning is a technique used to divide larger graphs into smaller subgraphs that can be processed independently, reducing overall computational complexity. Challenges in scaling out. While scaling out provides flexibility, it comes with challenges such as network latency, synchronization across nodes, higher infrastructure management costs, system memory considerations. Graph processing often requires large amount of memory. Scaling up ensures ample memory on a single node, whereas scaling out may involve distributing memory across several systems. Scaling up is vertical scaling. Scaling up means adding more memory, RAM, and processing power to a single machine. In the context of graph processing, this is beneficial if your graph data can fit entirely within the system's memory, as accessing data in memory is much faster than reading from disks. However, if your graphs are very large, the single machine might not be able to accommodate all the data despite increased memory. Same system memory consideration has scaling out, that is horizontal scaling. Scaling out means distributing the graph across multiple machines, each with its own memory. This can support much larger graphs. Each node only needs to load a portion of the graph into into its local memory. However, this distributes requires carefully consideration of network bandwidth and latency, as nodes need to communicate frequently during graph processing. Computational power needs. Graph processing benefits from high computational power, especially for real-time analysis. Scaling up may be suitable for CPU-bound tasks, while scaling out can help in distributing compute-heavy operations. Graph algorithms on scale up. Algorithms like discrete and BFS can take advantage of a powerful machine in scale up approach as they benefit from larger memory and CPU resources of a single system. Graph algorithms on scale out. Algorithms like PageRank and connected components, which operate on very large graphs, benefit from scale out strategies as they can be contributed across clusters of machines. Use case: social network analysis. Graph processing is crucial for social network analysis, where relationships between user form massive, complex networks. Scaling out is often required to handle the large scale graphs. Use case: fraud detection. In fraud detection, graph processes helps in finding patterns of malicious activity. Often a combination of scaling up and scaling out is used to meet the performance needs of real-time detection. Use case: recommendation systems. Recommendation systems often use graph-based techniques to suggest relevant items to of users. Scaling out is beneficial when dealing with a larger number of users and items. Cost cost consideration. Scaling up typically involves higher upfront hardware costs, while scaling out allows for gradual investment by adding commodity hardware over time. Performance trade-offs. Scaling up offers low latency operations, while scaling out may introduce network bottlenecks. The choice depends on the specific performance requirements of the application. Latency in scale up versus scale out. Latency in a crucial factor. Scale up minimizes latency within a single machine, while scale out may involve internet communication delays. Effective performance. Resilience in scale up versus scale out. Scale out architecture often provide better resilience through redundancy and failover mechanisms. Scaling up may introduce a single point failure. Example of scaling up systems: a high performance server with a large amount of RAM, multi-core processor, and fast store can handle moderate sized graphs using a scale approach. Example of a scale out system: a distributed cluster with many nodes connected over a network, whereas each node processes a part of the graph. In a common example of scale out system, hybrid approach, scale up and scale out. In some cases, combining both scale up and scale out approaches yield the best performance. Large graphs are partitioned and processed across the powerful nodes in a distributed systems. Emerging trends in graph processes. Recent advancements includes graph processing on GPUs, hybrid computing environments, and the use of in-memory processing systems for faster graph analytics. Cloud-based graph processing. Many organizations are moved to cloud-based graph processing systems, which allow elastic scaling depending on the workload demands. Case study: Google Prequel. Google Prequel is a distributed system designed specifically for large-scale graph processing. It demonstrates how scale-out approach can efficiently handle vast graph datasets. Case study: Apache Graph. Apache Graph, based on Google Prequel, is used for large-scale graph processing, commonly applied to social network graphs. Its scale-out approach shows how distributed systems are vital for big data. Final thoughts and future works. The future of graph processing lies in hybrid approaches, leveraging both upscale and scale up and scale out techniques, combined with new technologies like quantum computing and AI driven optimizations. Conclusion: the choice between scale up and scale out depends on the graph size, complexity, the performance requirements. For small real time graphs, scaling up may suffice suffer, while large scale graphs require scale out solutions. Thank you.